All right, guys, now that we have our implementation plan in place for Part 7, let's go ahead and jump over to Visual Studio Express and get the cells functioning.
All right, so let's jump over to Visual Studio. And the first thing that I want to focus on is the game class. We have some of these fields we were talking about, things like time until attack and cell attack interval. What I want to do is get all of these fields laid out so that we have them in place and ready to be used. So, let me jump up to the top of the game class, and let me jump in right below the enemy fields. And let me drop down a comment for cell. So we're going to put all of our cell-related fields here. The first of which is going to be the constant that describes how long it takes cells to die, or the cell death time. I'm going to make this a constant. I'm going to give it a type of float, and it's called cell death time. And I'm going to set this value to 2, because we want the cells to take 2 seconds to die.
Okay.
After that, I want to establish the healthy color and the dead color. Now, of course, colors can't be constants, so I'm just going to define these as private fields. So I'm going to make 2 private fields. I'm going to make them both static, and I'll get back to why in a second. They do need to be static for a specific reason, and we'll see that towards the end of this session. Now these are going to, of course, be colors, and they're going to be called cell. Let's see, the first we've got is healthy color. Cell healthy color, and I have a specific shade of green picked out from the original graphics that were created. So I'm going to make a new color and specify the RGB values. For the healthy color, that's going to be a red of 124, a green of 207, and a blue of 86. Alright, now since that was a somewhat lengthy line, I'm going to get lazy and copy that line for the cell dead color, so that I now have a private static color, cell dead color. And let's set that to an RGB value of 115, 59, and 141. And that will be our purple color. Alright, a few more fields. We need the timing fields. We've discussed the timing system that is going to be put into place, and that is going to be driven by the time until attack and the cell attack interval. I'm going to make both of these fields of type double because the time in total seconds is given in double. This way I don't have to cast back and forth, just store it in a field of the proper type.
Right.
So I'm going to make 2 fields. The first, double, next, attack.
Actually, we're going to call it time until attack.
I was looking at the right. Yeah, this is the first one. So this is going to be double time until attack. And
the next one's going to be our cell attack interval, which we'll go ahead and initialize it to.
Right, I was looking at like which one to initialize, which one was called which. But
yeah.
We've got time until attack and cell attack interval. Cell attack interval is going to be initialized to its value. Really, this is what you were talking about when you said that we could have made this one a constant, because we're not actually changing the cell attack interval in the code here. But since, changing the timing could be very interesting for a skill type thing, so we're going to leave it just as a field. So if you wanted to change it, it would be easy to.
Exactly. So now, following our implementation plan, the next thing we need to do is turn our attention to implementing this timing system using time until attack, making sure that it gets set to the cell attack interval, and then decrementing from it inside of the game class's update method in the playing section.
Okay. So I think that began with your saying that time until attack needs to be initialized when the game begins.
That's right.
Well, right now we don't have a begin method, but we do have load graphics content where we were plugging in this, if you want to call it, temporary state.
Yeah, that'll
so
work.
Let's do that initialization for time until attack. So time until attack gets set to a value of cell attack interval. There we go. Okay. So there we will have time until attack initialized. Now we need to turn our attention to updating that mechanism and decrementing the value when we're inside of update. So here's update for the game. Now, of course, we're interested in the playing state specifically.
So before the loop.
Yeah, right, before the update loop. So I'm going to jump in, add in a few blank lines so that I can decrement the time until attack. So time until attack minus equals the elapsed game time in total seconds. So we have game time. So we can get game time dot elapsed game time dot total seconds. So we'll decrement by the value, and that will have our time until attack set up.
And now what we need to do is turn our attention to this loop and check to see if we have a cell, and then we can put the rest of the code in place if it is indeed a cell.
All right, so let's jump into the actor loop. Now let's scroll down. Now we need to look for cells inside of this loop. This will be done in the same manner as when we were looking for enemies. When I was looking for enemies, I declared an enemy variable and then tried to cast the given actor as enemy. If it worked, there's our enemy. If it's null, then we don't have an enemy, so we need to skip on. And actually looking at that method, I'm going to do a pause for just a minute and do a slight correction to the method. Remember when we looked at player, we did a continue so we don't look on to anything else? I haven't yet put a continue inside of enemy.
Ah, good eye.
So let me drop that in real quick before we get back to coding the cell. So continue, and there we go. Of course, I'll need to remember to do the same thing inside of the cell code. But now, at this point, we've determined, if we're going through and looking at this actor, at this point, if we've gotten this far, we've determined that the actor is not a player. We've determined that it's not an enemy, so we can perform a check and see if it's a cell. So using the same method as enemy, I'm going to declare a cell variable called cell. And then we'll try to cast actor as a cell. Now if that worked, then the cell will not be null. So if cell is not equal to null, then we are indeed looking at a cell actor. So there's our check so we can find cells.
Okay.
Now we need to do those two things that were whiteboarded for update. And that is to check the attack time and see if this cell we're looking at needs to be attacked. So let's put that check in. And remember, that check is seeing if the time until attack has run out or is less than or equal to 0. So if time until attack is less than or equal to 0, and the state is healthy, because only healthy cells can be attacked. So and cell.state, looking for cell state, and yeah, there's a few down, so let state is equal to cell state dot healthy. And if this condition is true, we have our case for attacking a cell. So we actually launch the attack against the cell by calling the cell's setAttack method. SetAttack needs to take in a death rate, which we'll note that we have to change.
That's right.
But what we're looking for there is the cell death time. So I'm going to plug in the cell death time field we just created, a constant. So that will set off the attack. Now we need to set the time until attack, and we need to reset that value because we don't want to immediately go on to all the other cells. We want to wait a second before we even attempt to attack other cells. And that means we'll take our time until attack, set that back to the cell attack interval so that it has some time put back on it that has to be worn off. And that takes care of the attack code. Now we can turn our attention to the possibility of saving a cell, because there's one possibility that is a cell could get attacked. Another possibility, under the right conditions, are that this cell could be saved. So let's plug those conditions in. The condition for that is that the cell is already attacked and that it's being collided with the player. So that means if cell.state is equal to cellState.attacked and we're colliding with it. So and actor.check collision with this cell and the player. So once again using the player field for the check collision. So if we have this case, if we are attacked and we are colliding with the player, then it's time to save this cell. So we simply call cell.save. And then let me also jot down the note for the possibility of scoring. So we could say add to score here.
And then we'll go ahead and continue.
Oh yeah, and I was just about to forget that. So after we jump below these, we'll put in a continue because we have determined that this is indeed a cell, and if there was anything else, we can move on safely at this point.
Excellent. So now what we need to do is go ahead and, according to our implementation plan, turn our attention over to cell. But let's build real quick, make sure everything builds well.
I was about to say, let's make sure that I haven't induced any errors.
And very nice.
But we have a build succeeded.
So let's go ahead and turn our attention to the cell class and go ahead and fix that death rate real quick.
Right, let's change that field name. We had decided on a field name here
of time.
Death time. I don't think it's in use anywhere, but just in case, I'm going to refactor instead of just renaming it here. So we'll hit F2 and change death rate to death time. And yeah, there was only one place right here. But there we go. We now have death time instead of death rate as a field. Now we can move on with implementation.
Okay. Well, our implementation plan called for us first putting the code in place for setAttack, since that was the first thing we took a look at doing from the update method over in the game class.
All right. So moving down to setAttack. All right. First thing to do in here is the check. Make sure that we're healthy before we actually set the
And you
attack.
may be wondering, why are we putting this check in there since we just did the check over from update? This is more of just an interface where if anyone else was to call this method, I mean, it is indeed a public method and can be called. We want to make sure that the only way code gets executed in here is if the cell is guaranteed to be healthy, period. Okay?
So let's do that check. Let's do a check and say if this.state is equal to cell state.healthy, then we know we're good and the cell can indeed be attacked. So let me block that in. And now we can put whatever code we want here. Also, I've noticed that the parameter is also called death rate instead of death time. And the reason refactoring didn't hit that is because there's no link between these two. It's a different thing entirely. It's a parameter, not the field above.
Right.
But I do want to set both of them to death time. So now we can move on to the next line, and that is to remember and store that death time in the field. Or rather, this dot death time equals the parameter death time. And then the other thing we need to do is to set the cell state. So this dot cell state, state, will be set to cell state dot attacked.
Okay.
And that takes care of set attacked.
All right. Now the next thing we had done in the implementation plan was set up our save implementation.
All right. Let's jump down to save. And let's see. First thing is another check. We want to make sure that the cell is not already saved. So the check will be if this.state is not equal to cell state.saved, then we aren't saved yet, so we can execute a save.
That's right.
That will include doing the scale and then the setting of the state itself. So what we're going to do is start a scale. So of course, as soon as we have the save the cell, then we start that scale down to 0. So we're going to call this dot set scale.
Start scale.
Oh, excuse me, start scale, not set, but yeah. I was looking at set attack from above.
I got
kind
you.
of crossing the wires there. But we want to start a scale. We want to scale down to 0, so it's almost like a complete scale to invisible. So I'm going to give a scale target scale of 0, and a scale time. And for scale time, we're going to use that cell save time constant that should exist up here in cell. There's cell save time, so that's where we get the half a second save time for cells. But that will kick off a scale, and the next thing we need to do is to remember that the cell is saved. So we're going to set the state to cell state.saved. And there we have our state.
Very cool. Now our implementation plan called for us to turn our attention to update. But inside update, we know that we make use of 2 utility type methods, lerp and add enemy at. Let's go ahead and code those in real quick so that when we start coding in the implementation for the cells update, everything's in place.
Right, the picture will come together better because we know that, okay, that's exactly what's going to be happening here. So that means we could shift our focus now and we could turn, we could look at lerp and implement lerp,
okay,
which happens to be right below save. So inside of lerp, I'm going to erase the temporary return line so we can put in the real code. And this code is going to consist of, first, 4 different bytes to represent the components of a new color. And let's start with red. So I'm going to make a byte variable, which I'm going to call R. And now I want to set red to be the interpolated value of the red component from color 1 and color 2. And this will require use of the math helper. So if we take a look real quick, we've got math helper. It has a lerp method, but look at what lerp returns. It returns a float, and I want to store things in a byte, so I'm going to need to cast this to a byte in order to store it. But math helper lerp, we're going to need to take in 1 floating value, a second floating value, and a third floating value for an amount. Now I'm going to be feeding it bytes, but there should be no problems there since we're actually going to a larger data type, so there will be no data loss. So that means for the value 1, we want to go from color 1 to color 2 depending on amount. So let's see, let's look at color 1. Color 1 has its components, alpha, blue, green, and red. Here we're looking for the red component, so I'll plug in red for value 1. For value 2, that would simply be color 2's red or R component. And then finally the amount, we'll simply plug that in directly as the given parameter.
Look at the 2 M's. The 2 M's.
Maybe time for some refactoring. And much better.
Much.
All right. But that's it for red. Now we have 3 other components. So let me copy this line and then paste it a few times. So one's for blue, one's for green, one's for blue, and one's for alpha.
Okay.
So red will become green. Then looking at the color 1, we want the green component. Color 2, we want the green component. Because, I mean, if you miss any of these, that could yield some really interesting results if you cross some of the colors in the interpolation. But that will take care of green. Now we can look at blue, which will be the color's blue component, color 2's blue component, and finally alpha. So I'll make a byte A for the A component of color 1 and also of color 2.
You might want to point out the reason the color shift is going to be so predictable is because we're basically using a black and white image for the cell. So when we multiply it by the color...
Right, that is a good thing to point out, that the cell texture is a grayscale version of that cell texture. It doesn't already have some color. But that was very useful, because if we take a whitish or off-white color and then tint that, then we can get any desired color. That's how we did the actual color
Very
shift.
controlled, easily predictable color.
Right. But now here we've assembled the 4 components as 4 bytes, so let's package them back together into a new color. And while we're at it, we can just return that color. So I'm going to put in a return. So we'll return a new color, where we will take in the red, green, blue, and alpha components, packaged together and returned.
All right.
And that's it for lerp.
Okay. The other thing that we're going to need is going to be the add enemy at. And this is something that you had said in the last video that we were going to implement inside of the game class.
Right. And before we put that in, let me say exactly why it is we need to do that.
Okay.
Add enemy at is, of course, going to be called from update. So let me scroll up. It's going to be called within this method. Now, if you remember, the constructor for an enemy, let me actually switch over to enemy just for a second. The constructor for an enemy needs to take in a texture, a base speed, and a speed variation. That is required to create an enemy. Do we know about any of these things from Cell? Do we know about the enemy texture? So, for reference on that, let me jump to game 1 real quick. So we have, the only knowledge we have of enemy texture is right here in game, not in Cell. So what about the other things? Actually, let's look at making enemies here. What things are we using? Game 1.enemy texture, game 1.base enemy speed, game 1.enemy speed variation. Things we don't necessarily want to make ourselves dependent on inside of Cell. That's why we can't just create the enemy directly, because I mean that might be one consideration. Why not just make an enemy variable inside of update and set it? Well, we're missing some things. We don't know what texture, and we don't have those variables available to us. We could, however, tell the game, if we had a method inside of game 1, we could tell it to make an enemy, and here it has everything. These fields are defined, these constants, and this enemy texture is also a field of game. So this is why I want to create a method inside of the game class itself. So what I'm going to do is jump down below our utility methods region, and I'll make a region for this. Just in case I collapse all these, it'll make them all readable as small subsections.
Okay. I want to remind them, again, as we progress into more advanced code structures, this is not how we're going to be doing things in the future. Again, we're trying to utilize everything we've demonstrated to beginner programmers up until this point.
Right. I'm sure with some more advanced topics, we could handle this in a more
elegant way.
In a more elegant manner. But for here, this will work, and we'll keep it clean enough.
Mm-hmm.
So I'm going to make a region called enemy helper method, and this is where I'm going to add or create the add enemy at method. This method is going to be public, of course, since we need to call it from outside of game 1. It's going to be static, because I'm not storing an instance of the game anywhere else. It's going to be void, since we're not returning anything. I'm going to call it add enemy at. Now, add enemy at suggests that we need to take in a position. And I'm going to take in the position as a vector 2, which I will simply call position. And then we have, at this point, now we have everything that we need. We have the 3 fields for the constructor and the position, so that we get a specific positioning for this enemy.
Okay.
So this is the place where we can make an enemy variable, which I'm going to call enemy, and that will hold a reference to our newly created enemy. So here's where we need to fill in everything. We have the enemy texture as enemy. Where was that at? It's enemy. It's actually not wanting to show that one. Maybe it was just missing. I'm pretty sure that's up and above in the game class. But anyway, let's move on to base speed. I'll check it in a second when I build. But enemy base speed for the base speed parameter. Enemy speed variation for the speed variation, and that will result in a new enemy. Just because I'm curious about this, let me build and see if I need to track down any problems. Okay, I see what this is. I may have mentioned in the past that we would have to address enemy texture, that it was going to be static. And here's why. Or actually, here's why we're getting the error in this case. we're saying that we're inside of a static method attempting to use an instance field, which we can't do. So in order to correct this, I'm simply going to change this field, the enemy texture, to be static. This should cause no other problems because the instance version can see the static version no problem.
That's right.
We can't go the other way, though. We can't have a static version see an instance because it has no reference to that instance. So I've changed enemy texture to static. If I build now, that has corrected it. And that was also why it wasn't showing up in IntelliSense, is it was saying, it's like, look, that's not available to you here. But now that we have enemy texture plugged in, now we get to the whole point of this entire method, and that is the ability to set the position of this new enemy. So we can take enemy, and we can set its position to that position parameter. And that's it.
Let's go ahead and build, make sure everything's happy there.
And
now, with these methods in place, we can go back to cell and implement its update method.
All right, we have everything we need for update. So we'll go back to the cell class, and now we'll make sure that we're in the update method and jump up a few lines. All right, the first part of update that we want to take a look at is when the cell is attacked. So if this dot state is equal to cell state dot attacked, then we need to do a few things, beginning with the life percent. If we're attacked, that means our life is draining across time. So let's look at our life percent. As a matter of fact, I'll do this dot life percent. We need to decrement it. We're going to decrement it by an amount of time passed, but we have to consider the death time as well. And also looking at this, life percent is a float, and time is going to be in a double, so let me cast down to a float. And then I can look at game time. We're looking for elapsed game time in total seconds. Now that would be over 1 second. So let me factor in death time by dividing against this dot death time. Now if we divide against this dot death time, if death time were to hold a value of 2, that would mean if like a fraction of 1 second went past, that would be divided by 2, so less time would go by and the life would decrement more slowly. So that takes care of death time. Now that we've adjusted life percent, we have to look for the possibility that that life adjustment has just killed the cell. So let's do a check for death. So if life percent is less than or equal to 0, then this cell has died. And there's some things we need to take care of inside of here. One, we need to set the state. As this cell state is now equal to dead. Alright? Next thing we need to do is to decrement the cell counter, because now we've taken one cell out of play, so we need to set that here. So we'll say cell count minus minus in order to decrement it. Now, one thing left to do inside of cell death, and that is to spawn an enemy out of this cell. And for that, we need the add enemy at back in game 1. So we've got game 1.add enemy at, and now that we have add enemy at handling all this troublesome texture and parameter stuff, all we need to feed it is a vector 2, which we have. We, being an actor, have a position that we can feed to add enemy at.
Okay.
And that takes care of the death case. So let's jump down below that now. So, irrelevant of whether or not we died, there's one other thing we need to do, and that is to adjust the color of the cell over time. Since we are attacked, it means if we didn't die, then we need to be changing our color depending on how much life we have left. And we'll set the color by using the tint field. So this .tint equals the interpolation. Because of the tint now, we know we have a full healthy color and a full dead color and a life percent. So we have everything we need for lerp. So is that tint equals, let me put into this just to suggest where lerp resides. So we need to take in the two colors, and those are the dead color, the healthy color, and the amount which is given in life percent. So life percent will drive this interpolation between colors. And I believe that takes care of attacked. So in attacked, we do life percent, we check for death, and we adjust the color. So that takes us to the other thing we need to consider inside of update, and that is, has a saved cell disappeared off of the screen? So of course that's going to require a check of the state again. So I want this dot state, is it equal to cell state dot saved, and being saved, has it finished its scale? So is it saved and is it no longer scaling? So if not, this dot is scaling. So if that's the case, we're saved, we're no longer scaling, and it's time to remove from the list. So let's look at the actors list. So actors.remove, and feed it this. We also need to make sure that we update the cell tracker, the cell count, and take cell count and decrement it. Because if a cell was saved, it's no longer in play. Just like if it died, it's no longer in play.
Right. Very cool. Okay, so that's pretty much everything in place for update, and that puts the whole system for controlling death and getting saved and all that good stuff. Other than, let's see, I guess we can go ahead and shift our attention now to getting them spawn.
As a matter of fact, before we put in the method, let me see if I can manually create some. Because in
Sure.
enemy, we had created a new enemy before we had the add enemies method.
Okay.
So what I'm going to do is jump to the game and just make a new cell. But I think we might have an invisible cell. Looking at cell and looking at some of the things it uses to draw, I don't know, there's a few things to set, so it may or may not be
that's
visible.
a very good point, actually. In fact, I know for a fact there's a few things that need to be set if you want to go ahead and get those things set.
Just so that we don't have an invisible cell when we create them.
Yeah.
Let me jump back to cell, and what I'm talking about is some fields that are not yet initialized. When we created the constructor, we initialized healthy color and dead color, since those were obvious and given by parameters. Now there's some more things that should make sense. Things like the life percent, the state, and the tint.
Right.
So let's start with the life percent. So we want life percent to start off at 1. Otherwise, if we left it to default, cells would start out dead. We also want to set the state. So this dot state, let's set that to healthy, because cells start out healthy.
That's right.
And let's set the tint. So this dot tint equal to the healthy color. Otherwise, we might start out with a white or gray colored cell.
And since we know this will be a savable cell, let's go ahead and increment the cell count.
Right, you've noted that we've decremented cell count a few times. We've never actually incremented it. So what we're going to do is, since we want this system to be as automatic as possible, we'll just say that on cell construction or on cell creation, we automatically up this number. So we take this cell count. I was forgetting for a second that was static. Cell count is incremented on creating a new cell.
Okay. Now I think you're in better shape. So if you want to go ahead and see if you can make some.
All right, so I'll build, and fewer missing fields this time as we're starting to get things implemented. All right, now let's jump to game, and let's see what happens when we create a new cell. So I'm going to scroll back up to Load Graphics Content, and let's create a cell just before we create the player. So after, well, actually, let me do it before we even create enemies. I'm just thinking of the draw order and the creation order.
Sure.
But let's make a new cell. So new cell takes in a texture. Well, we need one of those before we even try to create a cell, so might be time to take a quick segue here and make a cell texture. And just like we've done for pretty much every actor, I'll just copy the field and change it to, say, cell texture. Then, of course, I need to load it, so I'll just duplicate the enemy texture line and change this to cell texture. And looking over here in our textures, we have a cell file, so we can use that cell asset. Alright, now we've got a cell texture. So back to creating a new cell. We need a texture, so we'll give it cell texture. We need a healthy color, which we have in the field for cell healthy color. We need a dead color, so we've got cell dead color, and that satisfies the constructor. So let's see what happens. So let's run. And there's a cell off in the corner, and I managed to die. So let me hit A.
And actually, not going to be able to hit A until I make a quick change for you, Logan. Hang tight real fast.
Oh, okay. We've made some changes to the controller setup.
Yeah, we sure have. We've actually unplugged that from the system.
Momentary pause for a second while we rectify
now you
the
should
input
get
situation.
a controller.
And with this controller now, A. Or did we not implement the input for dying? I thought we had put in. Let me scroll down.
Actually, I think we just sit there. No, I don't think so.
If we're dead, let me just do a quick thing. Oh, B, I was hitting A. Had I hit B, we might have been okay.
Yeah.
So let me run, and let me just try to avoid everything. Watch that cell in the corner.
Ta-da!
Changed to dead, and spawned an enemy.
That's fantastic. If you want to go and set its position to 200 by 200, everybody can see it a little bit easier.
Right. Let me, let's see. Back up. Now, back to Load Graphics Content momentarily. I'll temporarily make a variable. Ooh, wait, no, I won't. let me take this, not create a variable, take the constructor, which should have a reference, dot position.
There you go.
Equals, let's use the get random position. Game1 dot get random screen position. Padding. Oh yeah, this is why I didn't do this last time. What do we put for padding? How do we access the cell? Here I thought I was getting all slick.
Oh, just make something up, just for demonstration purposes only.
Okay, right. I'll give it 100.
There you go.
Well, more than enough to put. Oh well, and if I just followed what you had said and made it 200 by 200, I wouldn't even have to worry about that.
Oh, but that's all good. Let's see what we get.
All right, set random screen.
All
position.
right.
There we have it. Well,
And he started to die. He's dying, and look at
and there's
that.
the enemy.
Fantastic. And now there's more enemies. So
that works. Now, so that we've proven that the cell code, both the attack code and the death and enemy code is working, now we have a need for add cells, because adding each cell individually like this would eventually become tedious.
that's right.
So it'd be very convenient to have the add cells method back in the cell class. So once again back to cell. If we scroll all the way to the bottom of the cell class, here we have the skeleton for add cells. So let's take a look at this, and let's put in that first loop, the outer loop that takes into account the number of cells. So I'm going to drop down a for statement. I'm going to use the template, so tab twice, I get everything filled in, and I'll replace length with num cells. Alright, now inside of this loop, we need to make cells. And here I am going to make a cell variable just for convenience and readability's sake. And for later when we need to worry about positioning. So I'll make a cell variable. Then I'll set that equal to a new cell, a new instance of cell. We have everything we need provided to us, so I'll feed in the texture required, the healthy color, and the dead color. That will result in a new cell, and as we saw just a second ago, positioned at 0, 0. So let's change that to be random. Let's turn around and use that new cell reference, set its position to be equal to game1 dot get random screen position, and now I have an accurate padding that I can pull from this cell's radius, and that will result in a new cell. And we have the loop driven by num cells, so at this point I could go back to game and try it out. I know there's more stuff we'll have to add, but this will have the beginning set up. So we could do cell dot add cells, and we should take in a number of cells. Let's start out with 5. Excuse me, and then the rest of it is the texture, healthy color, and dead color.
And go down a couple lines and change the number of enemies down to like 2, just so you're not having to scurry
right,
so
just
much.
to make it easier. I could even take the enemies out. Also, I had kind of hacked this line together from what I had originally. I still have the dot position set, and with that add cells not having a return, that could cause problems. So let's just not have that happen. And for simplicity's sake, I'll comment out enemies for the time being.
Oh, okay.
So let's run and see if we get 5 cells now. And we do indeed
and one's
get 5.
dying.
And now we can see the... forgot about that part. Now we can see that the attack is stepped, meaning we go cell by cell in order for the attack. As a matter of fact, let me see if I can break the mechanism just to show some of those cases we were talking about, some of those possibilities we were avoiding. What if we took out the check of healthy? What if we just went by time only? Let me see. Or let's see. Do I want to do that first? There's a few ways.
You can take out the time until attack being reset back to the cell attack interval.
There's a few fun ways we could break it. If we take the time until attack out.
And here we go. And they all die.
All of the cells die at the same time. So that's what we were talking about, where after an attack, we need to set the attack time so that we wait before attacking another cell. Otherwise, we attack them all at the same time. So just wanted to point that out. So back to the cell positioning. Everything's looking pretty good.
Now let's start adding a lot more cells in.
Right. So
oh, well, there you go. You've already got 2 that are overlapping.
So those 2 on the side are kind of overlapping. So let's increase the chance of that. Let's create maybe 50 cells.
Ooh.
And look at what's happening here. We have a lot of overlapping in many of the different areas of the screen.
And it's about to be very difficult in a minute.
You know, even if I had fewer, it might do that. Even at 20, yeah,
Yep.
even at 20, we have quite a few cases where we have cells that overlap each other. So let's see what we can do about fixing that to make the board look much nicer. Let's go back to cell once again, and let's enhance the add cells method.
And to do this, we're going to need to make a call over to check collision with any, something we talked about when we were setting up the implementation
we want to
plan.
get that running first so that we have its...
Yep, it makes more sense. Oh, hang on. Let's see if you can undo what I just managed to hit.
Oh, one of the nice Photoshop links has relevance to Visual Studio.
That's awesome. Not really.
But yeah, it's...
Wiped out all your code. Okay.
Let me get that saved again.
Let's
Game,
see. What else have I?
Cell dot position.
Hey, ta-da!
I think you had hit one, and then I had hit some button, or maybe that thing had more shortcuts.
Okay, so let's go ahead and this thing has more shortcuts, I guarantee you. Let's go ahead and go to the actor class now.
Right, because this cell placement check that we're going to put in is going to be dependent on check collision with any. We need to have that working in order for our placement to work. So here in actor, in the collision section, we have the check collision with any, which is just a skeleton. So I'm going to jump into it, and I want to push the return false down. That's going to be part of it in the end, but we need to put the bulk of the code in place. And that is a look through each of the actors.
Mm-hmm.
And I guess just for brevity's sake, I could use a for each in that. So we could do for each, let's say actor in the actors.
Well, that's for each
list.
actor. We need to go ahead and give our variable name.
All right, I haven't even made a variable, and it's quick to highlight that. For each actor in actors, do the following. All right, so with each actor pulled out of the list, looked at individually, the first thing we need to do before we do a check collision is make sure that the actor we've just gotten out is not the actor that this instance belongs to.
Right.
So that means you check to make sure that if actor does not equal this.
Ourselves.
Because we don't want to collision check against ourselves. If that is indeed the case, if it's not this actor, then we can do a check collision with this actor against whichever actor it pulled out of the list. So that would be a check of if check collision between this and the given actor. If that is indeed the case, then we have found a collision with one of the actors and can return true. So I'll put in a return for true, and there's no need to look any farther. We have indeed found an actor, so we can return.
And we have a return false at the bottom, so we're good.
All right, I've left that in place. So if this loop finishes and we never get to a collision, we return false after the method is done.
All right, so now we can go back over to our cells class, jump back down to add cells, and enhance it by putting an inner loop in that is going to allow us to continually try replacing a cell until we find a good place for it.
Right. For this, I'm going to use a do loop, because, of course, in a do loop, it will run at least one iteration.
That's right.
And that's very important here, because I want the position to get set at least once. Because what if this position was, in fact, valid? I want it to get placed once, and if it is, in fact, valid, we'll continue on. Otherwise, we'll start looping. So this is the line in question that we're looking at. Now, I'm also going to put in the counter variable. So I'm going to put in an int for counter, and let's initialize that to 0. Because, of course, with our loop now trying to reposition cells, we don't ever want it to get into a runaway scenario and lock the game. All right, so let's begin the do loop. So right after the counter, I'm going to start a do loop, and then block in this line here, end the block, and move that over. So what we're going to do is we're going to do this line while, and then some condition. So this condition is going to be, have we collided with anything? Then we need to replace it, or to check placement again. So while cell.check collision with any, and then we need to take a look and put in the counter check to make sure we don't get into the runaway scenario. So and counter is less than the cell placement retry count, that constant created inside of the cell class. Alright, so looking at that, everything looks good. Let me build, make sure that there's no errors in it. So there we go. A few things done, and a compound check, but this should get everything we need accomplished. 1, we set a counter. Next, we start a loop. Inside of that loop, we position the cell randomly on the screen. As soon as we position it, we turn around and we do a check. Is this cell colliding with any other actor?
And as long as it is,
if that's true, we go back up in the do loop and we position it again.
And that is, of course, as long as the counter is less than the cell placement. So we need to make sure we increment that counter.
I just noticed that we're not incrementing the cell counter. So along with the position, we'll take counter and increment it. So now each iteration through, we're not only repositioning, but we're incrementing counter.
So as long as we're colliding with some other cell, and our counter is less than the cell placement recount, we'll continue to replace that cell.
Right. So that means either until we get a good location, or we run out of attempts in order to try placing the cell.
Exactly.
So all that's looking good. Let me do a build, make sure that the code builds, And I believe it's ready to test. If you remember before, we had the 20 cells, and a lot of them were overlapping. Now if we run, look at that. No overlapping
Much
cells.
nicer.
So let's try this again.
Very nice.
Still nice. And again. So there we go.
Excellent.
And let me even try turning up the cell count now. What about 50? Can we do 50? Hey, look at that.
Much better.
Can we do 100?
Ooh, now you're going to push it.
A little bit of a pause at the beginning there, because we have a lot of cells, and you'll notice some of them over here in the corner.
Just a few, yeah.
They're overlapping, but I mean, looking at the screen visually, it did get to the point where there was probably very few locations it could have tried, and the random just wasn't finding the location in time.
Ooh, finally died.
Now, in order to give a good test case for why we need the retry count, let me up this to 1,000. 1,000 cells.
Momentary pause.
Notice the pause when the game launches. So there was a significant calculation required for this to happen. And, well, I mean, looking at the cells, that would be an insane cell field.
You know how good you'd be to have to get to this spot?
But what I like about showing this is that shows that the retry count of 100 does indeed make it so we could get to a ridiculous level.
Right.
And still have code that doesn't lock up. Yes, there was a delay, but still, I wouldn't even consider this a realistic scenario. But it is nice to know that the code will handle it and not lock up.
Right. And I'm trying to avoid. Okay, I lose.
And one other thing I noticed is I spawned over one of the cells and I was actually able to save it. Let me bring the cell count back down because we haven't tested that yet. We have a good field of cells. We saw that they all died in order. We didn't actually try saving any of them. Okay. So I'm going to bring the cell count down to a more sane 20 cells. Still quite a few.
Who's get him. Got him.
Oh, look at that.
Up two.
Missed that one.
Whoa.
Missed that one.
It's so hard without
life bars.
It's
yeah,
critical. It's so hard to see. There we go.
But the cells, when any cell saved in time is in fact working. It goes away, scales off of the screen, and no enemy is spawned.
Wow, this is really challenging. Okay, and now since we can't change states, I'm in trouble. Whee!
There is, just thinking about this from a testing and debugging standpoint, I do want to make sure that one part of the whole cell is working. And that is, remember back in save, or was it... what I'm getting at is there was a scale to 0 and then a removal from the list. Two entirely different things that would result in the cell disappearing visually. Okay. What I want to do is I want to prove that this, over an update, when we do this check and remove it from the list, we know that this will most certainly make it invisible because removing it from the list and we'll no longer draw it. But there's no way to tell the difference between a scale of 0 and this line being run. So let me come up with a way to test that. And I think what I could do is inside of save, what if we scale to something else, like only 0.5?
Okay.
So that way what we should see is a scale to something still visible and then blink out of existence. Let's see if that works.
You're still checking for a scale to 0, aren't you? No, it's scaling.
And let me find one to save.
And there it goes.
So
for a second I was thinking, wait a minute, you're checking to 0, but no, you're checking to see if it is scaling.
But that is also working. So you can see the cell disappear when it reaches a scale of half.
Outstanding.
So I just wanted to prove and make sure that code was working because this is going to be important since along with that removal from the list, if I scroll back up to update, and here, along with this removal, more importantly, we have the cell count that needs to be tracked. But that means that we are indeed hitting this line. We saw the cell blink out of existence, so cell count is indeed getting decremented.
Very cool.
And I've set the scale back to 0, so we have our visual effect back to the way it should be. So really, I think that's getting close to the end for cells.
Excellent.
And
all right, so is that pretty much going to wrap up this section?
That's all I can think of. If we've finished to the end of the implementation plan, everything we've tested so far is working.
All right, well, that's going to do it then. So that's going to wrap up this section, guys. Thanks a lot.